So that'd be a bomb calorimeter. But then for constant pressure calorimetry, it's actually easier. And this is one of the reasons why we use enthalpy instead of energy. If it's at constant pressure, then what you could do is just do something in a coffee cup. Where you get styrofoam cups. The reason you have styrofoam cups is you want something that's quite insulating and also that's quite light, that has very little mass. So when it heats stuff up, it heats up just what's inside of it. So you can have a little glass stirrer to make sure everything gets stirred up and the water, the hot water rapidly mixes with the rest of the water, so it's all one temperature. Have some sort of loose fitting cork lid to absorb to insulate as well. And you have two nested styrofoam cups containing reactants and solutions. And this works pretty well. There's a video where we have somebody actually doing the experiment in the lab of trying to measure a heat of reaction with a coffee cup calorimeter. So in this case, the heat of this, you assume that the heat of solution is everything. You could include the calorimeter, we'll get to that. So Q solution equals the mass of solution times the specific heat of solution times delta T. And the Q solution is just minus Q reaction, since the thing that's heating up is just the water. The solution, the water is what's being heated up by the reaction. You could include, if you want to be very precise, you'd want to include the heat capacity of the calorimeter as well, but in this case, there's not really, it's pretty negligible in most cases if you have a moderate volume of water. The styrofoam is light and it does not absorb the heat that well. So if you do it quickly. So that's the sort of calculation we do. So we have 50 milliliters of 0.1 molar silver nitrate combined with 40 milliliters of 0.2 molar hydrochloric acid in a coffee cup calorimeter. The temperature rises from 23.4 degrees C to 24.3 degrees C. Estimate the heat of reaction, and the reaction is silver nitrate plus hydrochloric acid goes to silver chloride, which we know is a solid that precipitates out, and nitric acid. So the first thing we need to do is figure out how many moles are actually reacting. So we've got 0.05 liters of silver nitrate, and the molarity is 0.1 moles per liter, and then we would get for AgNO3 1 mole of silver nitrate, we get 1 mole of AgCl, so that cancels, we get 0.005 mole of product, whereas if we look at the hydrochloric acid, 0.04 liters HCl times 1.2 moles per liter is the molarity, and that the liters cancel here, and we get, and then here also a stoichiometric ratio is 1 mole of HCl produces 1 mole of Cl, and this cancels 0.008 mole of product. So this is the limiting reactant, and so that's the amount of reaction that occurs. The rest of the hydrochloric acid is just sitting around. So what we have is, that's the total number of moles of product. So we know that the Q is going to be the specific heat of solution. And here we have a relatively dilute solution. We can assume that the specific heat will be approximately that of water. And there's a coffee cup calorimeter, right? It's not going to be that precise. So it's 4.18 joules per gram degree C. And again, this is a coffee cup calorimeter. How much does it weigh? Well, it's going to weigh it's mostly water, right? The solution is mostly water. And so we can assume that it's going to be 1 gram per milliliter. And we have 50 milliliters plus 40 milliliters, 90 milliliters. And then we have our change in temperature is 24.3 minus 23.4 equals 0.9 degrees C. So 0.9 degrees C. The degrees C cancel out, the milliliters cancel out, the grams cancel out, and leave us with 338.6 joules. It's more significant digits that we have. We'll get there in a second. And so we have our delta H of reaction is going to be, per mole, it's going to be, let's convert this to kilojoules. So this is 0.3386 kilojoules. We have 0.338 kilojoules. And this is minus now because this is this Q is the Q of the calorimeter. The Q of reaction is going to be the Q of reaction is going to be minus the Q of the calorimeter. And so we have 0.005. That's the number of moles of the reaction that occurred, the moles of the reaction as written there. So we get minus 68 kilojoules per mole. So that would be the heat of the molar heat of reaction here. And again, it heats the system up, so clearly it's going to be an exothermic reaction. All right, that's the end of this segment.